Okay, hello everybody. Today we'll be talking about work done by electric fields. So basically, to know how, like, about work done by electric fields, a little, it's desirable to know about like work done by gravity first, by gravitational fields, because that's a bit easier. Because gravitational field only points in one direction, that's down. So let's say if this is direction of gravitational field, as this is really obvious because gravity pulls things down. So the direction of gravity, if you take, like, let's say a mass and you move it to the right, you move it to the left, I mean, the work done by gravity is zero because you're moving the mass perpendicular to the direction of gravity. But let's say if you have a mass, another mass, and you move it anti-parallel to the direction of the gravitational field, like this, you do positive work. There's no work done by gravity. There's no work done, I mean, by gravity, because gravity is not doing the work, but you're doing the work. So if you do the work, if you're doing the work, you do positive work. But let's say if you have another mass like this, and you just let it drop, the gravitational field will do work on this mass. And the gravitational, we say that the magnitude, I mean direction, we say that you're doing negative work if you let gravity do, if you let the mass go in the direction of the gravitational field. So knowing this gives us a gist on like electric fields and work done by electric fields. So we could erase this. So what if you have, I'm gonna make it a little complicated though, just a little, not that you can't understand. Let's say you have a charge. Let's say it's a positive charge. It's kind of, is it's important that it's a positive charge. And then let's say the positive charge is moving like this at an angle theta. And let's say the electric fields all point uh this way. Let's say this is the direction of the electric field. So let's label this E. So in this case, what's the work done by the electric fields? Basically, if this positive charge is moving like this, the component of the velocity that's moving, the component of this velocity that's moving parallel to the electric field is the work done by the electric field. So basically you could break this up into components like this, and this component, which is this component that's moving in the same direction as the electric field, will be the work done by the electric field. So let's say, the since we know work is basically force times distance, and we also know that the force, the electric field force, I mean, equal to E, the electric field vector, times the magnitude of the charge. So if you replace this with this, you get that the work done by the electric field equals E Q times distance. So if, let's say, this charge moves like at an angle, and let's say this is the distance r that the charge traveled, and it travels this distance at this angle, the component of the distance parallel that's parallel to the electric field is, you, and let's say this is the component of, say this is the component of the distance that's parallel to the electric field, then the work done by the electric field would be, and since it's moving in the direction of the electric field, it would be negative. So you say that the work done by the electric field would be negative time negative E times the magnitude of the charge times R cosine theta. R cosine theta. And this would be the magnitude of, this would be the work done by the electric field. If it's moving, let's say if this charge, so if this charge was, say, moving up, then it would be doing positive work. Then you'll be doing positive work. And if it's moving up at this angle, the component of the electric field, the component of the distance, let's say that's pointing parallel to the electric field, is actually sine theta in this case. Okay, so this is how you deal with work done by electric field.